Dear children, you learned about gas laws, Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law. Gases which obey these gas laws at all conditions of temperature and pressure are called ideal gases. Ideal gases obey these gas laws at all temperature and pressure. But such a gas is hypothetical. No gases are ideal. Real gases show deviation from gas law at some temperature and pressure. Means real gases do not obey gas laws at all temperature and pressure. Now we are going to derive an equation for ideal gases. An equation to explain the behavior of ideal gases. This is known as ideal gas equation. This equation is derived from the gas laws. According to Boyle's law, volume of a fixed amount of gas vary inversely proportional to pressure at constant temperature and fixed amount, that is number of mole. At constant temperature and number of moles, volume vary inversely with the pressure. This is Boyle's law. Now according to Charles' law, volume vary directly with the temperature at constant pressure and number of mole. This is Charles' law. Now according to Avogadro's law, volume vary directly with the number of moles at constant temperature and pressure. This is Avogadro's law. Combining these three laws, we can write volume of the gas is proportional to 1 by P T into N. That is, volume is equal to, there comes a proportionality constant. Let the proportionality constant is denoted by capital R. R N T by P. P is taken to the left hand side, so the equation becomes P into V is equal to N R T. This equation is known as ideal gas equation, where P is the pressure of the gas, V its volume, N is the number of moles, R is the proportionality constant. This is known as ideal gas constant or universal gas constant. T is the temperature in Kelvin. The universal gas constant or gas constant R can be written as R is equal to PV divided by NT. This is gas constant. It is same for all gases. That's why it is called universal gas constant. This equation is called ideal gas equation. Ideal gases obey this equation at all temperature and pressures. But real gases show deviation from ideal behavior. Now the value of universal gas constant R can be calculated. For a fixed amount of gas, let the number of moles be 1 mole. If we have taken 1 mole of a gas, number of mole equal to 1 mole, and the temperature and pressure standard condition means standard temperature and pressure, STP. At STP, the conditions are temperature is equal to 273.15 Kelvin. Pressure is equal to 1 bar. The volume, we know that for 1 mole of any gas at standard temperature and pressure occupy a volume of 22.7 liter. Substituting all these values in this equation, we can calculate the value of universal gas constant R. That is pressure 1 bar, volume 22.7, that is the molar volume, divided by 1 mole. Number of mole we have taken 1 mole into temperature, standard temperature 273.15 Kelvin. We get the value for universal gas constant as 0.08314 bar liter per Kelvin per mole. Bar liter per Kelvin per mole. This is the value we obtain, or this can be written as 8.314 into 10 raised to minus 2 bar liter per Kelvin per mole. This can also be written in another unit. This is equivalent to 8.314 joule per Kelvin per mole. If the standard pressure is taken as 1 atmosphere, if the standard pressure is taken as 1 atmosphere, the value of universal gas constant obtained will be 8.205 into 10 to the power minus 2 liter atmosphere per Kelvin per mole. So depending upon the unit, there is slight variation in the value of universal gas constant. This is constant for all gases, means same value for all gases. Now rearranging this ideal gas equation, PV equal to nRT, we get PV by T is equal to nR. R is the gas constant for a fixed amount of gas. N is also constant. So PV by T is a constant. For a fixed amount of gas, we can write pressure into volume by temperature is a constant for a fixed amount of gas. So if we have a gas at a pressure of P1, an ideal gas with pressure P1, volume V1, temperature T1, changed to pressure P2, volume V2 and the final temperature T2, we can write P1 V1 by T1 will be equal to P2 V2 by T2. Here there are 6 variables given in this equation. Out of 6 variables, if 5 are given, the unknown variable can be calculated. This equation is called combined gas law. The ideal gas equation describes the state of a gas. Hence, this ideal gas equation is also known as equation of state. Now, we can derive a relationship between molar mass of a gas and its density. Means from ideal gas equation we can derive the relation between molar mass of the gas with its density and molar mass. Let's write the ideal gas equation, that is PV equal to nRT. So this equation contains no molar mass, no term for density. So we substitute n here. N is equal to, n the number of mole, n is equal to given mass divided by molar mass. Given mass is denoted by small m, molar mass by capital M. Substitute number of moles as mass by molar mass in ideal gas equation. We get mass by molar mass into RT. This equation, if we write P is equal to, volume is taken to the right side, so volume go to the denominator, M by V into M RT. We know that mass by volume. What is mass by volume? Density. Density is equal to mass by volume. So this can be substituted as density. dRT divided by molar mass. Or we can write this, molar mass is equal to density into RT divided by pressure. So we got a relationship between molar mass and the density of the gas. As you can see here, density and molar mass directly related. Higher the molar mass of the gas, higher the density. So we derived the relation between molar mass and density from ideal gas equation.